Okay, so hopefully everybody is here. Some people might have been confused and it's in the other room, but we're here. So let's try this room. And if this room is good, I'll send out the poll after this class so you guys can decide which room you like. Um, and you'll have an opportunity to give feedback on like why you like the choice that you like. So some people, this location might be kind of too far. So I don't know if that's, but I only will switch it if a lot of people really like this room better. Um, I don't think I'm that tall, so you probably can see the bottom of this screen. Um, so the test will only cover up to mixtures, and we finished mixtures. So we're moving to new material that won't get covered on this next test, but will get covered in the second test. And the way I break it down is like the first test is everything about first order differential equations. And we're now moving to second order differential equations. And we know that this is second order because we see here that there's a second derivative in the equation. So this second derivative, this is what makes it second order. We talked about this at the beginning of the semester, but the fact that there's a second derivative instead of just a first derivative makes this differential equation a second order differential equation, but we still want to keep the equation linear. Linear is going to be because you have a linear polynomial in the dependent variable and its derivatives. So that just means that you have um, all your x's, your dx's, dx over dt, and d2x over dt squared, all of those appear to a power of 1. That's what it means to be linear. So you can't have like something like quadratic like this. So for instance, you can't have a term that looks like dx over dt squared, for instance. That's not linear. So I'll just say we're not looking at things like this. It's not linear. So linear means that all your derivatives and your unknown solution variable appear linearly as a linear polynomial. So this is not linear. However, so this having a squared is not linear. However, these functions right here, which are all your q. Now we used to have just one coefficient, but now we have a p of t and a q of t and a f of t here. These don't have to be linear, so these can be nonlinear. They can be whatever you want. So like you could have like square root of x or sine of, oh no, you can have like not x. These can be like these are functions of t. So for instance, e.g., these could be like square root of x or sine of x, sine of t. They have to be t, square root of t or sine of t. So the functions of t can be nonlinear, but the x's have to be linear. So by eventually we'll be able to solve all differential equations that are second order with non-constant with these like coefficients for these functions of t that are coefficients of the derivative or x, and the right hand side can be anything. But to start, we're going to simplify things and just look at, first of all, equations that are homogeneous. So we'll eventually move on to have an f of t that's not 0. But initially, let's just look at only homogeneous differential equations. And on top of that, let's also look at the case where all the coefficients in front of your x and x prime and x double prime, these are constant. So we'll look at the simplified case where your right-hand side is 0, and then all the coefficients, although the P of t and the Q of t can be non-zero, non-constant, they are going to be constant for the first cases we're going to look at. So this is called again, it's homogeneous. So I'll just note that it's homogeneous. We're going to look at linear still. They're all going to be linear in this course. Second order. So that's coming from the fact that there is a second derivative here. So second order. It's going to be again homogeneous. But the main thing is that it's also got constant coefficient differential equation. So these are the constant coefficients. And so this special case is easier to solve because there are some, obviously simplifications done to the equation. But we should be able to solve the version up on the top here eventually. This top will have non-homogeneous potentially and then non-constant coefficient. But we're looking at this special case. So before we jump into this special case of having a second, this is a second order homogeneous differential equation, linear constant coefficient. We can go back and recall what was it for first order. So we've done this before. This is a first order homogeneous, like the right-hand side is 0. And you had constant coefficient. So we've done this case, and let's just revisit what was it like when we first had the first order case. So again, this case constant. And we notice that by separation of variables, this homogeneous solution where the 0 on the right-hand side was basically just reading off the left-hand side. So if you see this plus kx, it would have been c e to the negative kt. And we did that by separation of variables. Another approach, so like for example, this one, we already know the solution to this would have been c e to the negative 4t, right? Because that's because you just read off the plus 4x and it would have been negative 4t. And we did that by separation of variables, but so I'll just say homogeneous because it's got a 0 here. But unfortunately, we can't do separation of variables with a second order equation. So this homogeneous problem for first order, we were able to get by separation of variables. You notice that there was always a pattern. It was always like this. But we can't do that with a second order equation. We can't do separation. So the book does this. They say, okay, rather than separation is also possible, but another approach would have been to make an observation that you can, kind of like the method of undetermined coefficients, you can propose a solution form that looks like would work for this. So of course, if you make the solution x is equal to 0 will work all the time because derivative of 0 is 0 and 4 times 0 is also 0. But that's not interesting. Let's look at a non-zero solution. You might propose that a solution would look like c e to the rt. Why does this make sense? Because if you plug in an exponential into this derivative, you would get, of course, because of the chain rule, the r will pop out, but you'll still have e to the rt. And then, of course, if you plug in c e to the rt into this x, you'll also have an e to the rt. And then both terms will have e to the rt. And the question is, can I figure out, constants for c and r that will get the left-hand side to add up to 0? And so this solution form is not surprising as, and we clearly see that that's what we get at the end anyways, but you might say, well, I don't know exactly what the c and r's are, but let's propose that it's going to be something of this form, because if I plug this into the derivative, you get e to the rt. Plug it into the x, you also get e to the rt, and it's a matter of finding the c's and r's that would make them add up to 0. So we say this might be a good solution form, and like we've done before, we just plug it in. So you plug in this into the derivative term. If you do that, then there's a chain rule because the only variable is t. And of course, the derivative is with respect to t. So you're going to have a c times the r pops out because that's from the chain rule, e to the rt, plus 4 times, you're just plugging this in directly into the x, so c e to the rt. And then the hope is that we can find c's and r's that will get this to make this be true. I'm just trying to force this to be true. So you can factor out a c and an e to the rt. That's common between both of them. So c e to the rt is common between both. That leaves, in the first term, that leaves just an r left. And then this term will leave a 4. And this will have to equal 0. Of course, there is one obvious thing. You can make c equal to 0. Because if you make c equal to 0, then that's 0 times all this, and you get a true statement. But then if you made c equal to 0, that means you're saying that your homogeneous solution is just 0. That's always going to work, but we said that those are called 0 solutions. So the book actually says those are called trivial solutions. So let's just say we're not interested in trivial solutions, because if you make c equal to 0, then this homogeneous solution just be 0. And 0 will work because 0's derivative is 0. 4 times 0 is also 0. But let's say c is not 0 for to obtain non-trivial solutions, so-called non-zero, non-trivial solutions. In that case, the only thing that is left is to make the r plus 4 equal to 0. And that, therefore, will mean that r has to equal -4. And you can see that, okay, well, if r is equal to -4, then our homogeneous solution was x of h is equal to c e to the -4t, which agrees with the separation of variables solution we had before. So this solution form can be forced to satisfy this differential equation if you make r equal to -4. And this solution form was not that much of a stretch to think that this would be a good solution form, because this is the way that you can get your two terms on the left-hand side of this equation to contain e to the rt, where you might find c's and r's that will get the left-hand side to equal 0. C equal to 0 will be one of the solutions. R is equal to -4 will be the other one. But c equal to 0 is not the interesting one, because if you make c equal to 0, then the homogeneous solution just be equal to 0, and that's called the trivial solution. And that will always solve any of these differential equations. The zeros will always be able to, any homogeneous equation will be could be solved by using 0 for your solution. So because you can't do the separation of variables on a second order equation like this, we are going to use that approach. We're going to propose that a good solution form for this second order equation is going to be the same thing that we proposed before. So I'll just say this right here. And so we'll propose that the solution form would also be an exponential of this form with some e to the rt that we're going to figure out. This c to the rt, again, doesn't seem like a stretch, because if you plug it into your x, you get an e to the rt. If you plug it into x prime, there's a derivative with a chain rule, but you'll still have an e to the rt. And plugging it into double prime will still have an e to the rt as well. So every single term on the left-hand side will have e to the rt. And then the rule of the game is to try to figure out the r that will end up causing all the terms on the left-hand side to cancel each other out. So if you propose that the solution is of this form, then you can take the derivative of it, which is going to equal CR e to the RT. And then you can take the second derivative of it, which is going to equal CR squared e to the RT, because chain rule pops these out. And then we plug it in. Of course, the second derivative, there's an a in the front, so I'll say a times this thing, which is the capital C r squared e to the RT, plus the b is going to have a multiplication with this first derivative, capital C r e to the rt plus the c. Okay, so it's confusing, but this is a little c, so I'll make it really small. And then this is a capital C, e to the rt. And this has to equal 0. Again, there's stuff that's common across all three of these terms. What's common is a capital C, e to the rt. So you'll have capital C, e to the rt. And then the first one will have a r squared left after you factor that out, plus the second one will have a br left, and the third one will have just a little c left. And this has to equal 0. Again, I'll just say that we don't want c to equal 0. So we'll just say c does not equal 0 for non-trivial solutions. Non-trivial solutions. So that's like to say that this c here, as well as this c, we're just going to say is not 0, which leaves us with the only thing left is to make this thing in the parentheses here, ar, well, I'll just copy it, this ar squared plus br plus c, that equal to 0 will be the only other way to force this solution form to satisfy this differential equation. And unlike the previous one where we had a first order equation, that would just said that your r plus 4 had to equal 0. Your second order case has a quadratic equation that has to be satisfied. And so up here, we only had one solution. We had that r had to equal -4 was the only way that you can get this to satisfy this differential equation. This looks like there are two r's that in general may work because it's this, solution to a quadratic equation. So that's going to be the case for second order equations. You could have up to two different r's that will make this solution, this homogeneous solution form satisfy this differential. In other words, there are two homogeneous solutions instead of one homogeneous solution. They have one for one of the r's and another one for the other r. And this green box is called the characteristic equation. And some people call this piece, which is the left-hand piece, just the characteristic polynomial. And the equation is just because it has equals 0, but if you just looked at the left-hand parts. So the roots of this give r such that, okay, so I'll just write that. Roots of this give r such that e to the c equals c e to the rt is a homogeneous solution. Okay. So we can use this to solve, for instance, what's the homogeneous solution to this differential equation right here. Again, we are just going to use this observation that, okay, we'll just say here that you have x is equal to c e to the rt. Of course, the first derivative is going to be c e to the cr e to the rt. And then the second derivative is cr squared e to the rt. And if you plug this into this differential equation, the first derivative is cr squared e to the rt minus the x prime is cr e to the rt minus 2 times c e to the rt. This is equal to 0. You can divide everything by, or you can factor out everything, factor out a c e to the rt. You're left with r squared. minus r minus 2 is equal to 0. And this will only happen if you had this thing, r squared minus r minus 2 to equal 0, which it can be factored into r minus 2 and r plus 1 equals 0. So you get, therefore, r is, well, there's an r1, it's equal to 2, and an r2 that's equal to negative 1. I'm just labeling the two roots of this. And you've got two homogeneous solutions. And I'll show this in a moment, but the general homogeneous solution to this differential equation will equal, so I'll just say xh, will equal, so there's going to be one solution from the first one, which is going to be c e to the 2t. That's like plugging into this r. The other one's going to be c e to the negative t. And they're just coming from each of these. And this one right here. Let's do this. And I'm going to also say that in general, these constants may not be the same. So I'll just say this one's C1 and this one's C2. And so the general homogeneous solution ends up being just the sum of the two homogeneous solutions. And this will be the general form of the solution and will also satisfy this differential equation, which I can show in a moment. So you have your characteristic equation, which is right here, which is quadratic. You get two r's and you get two homogeneous solutions. And then the general homogeneous solution is just adding them together with these two constants not necessarily being the same. That's just as a summary. So this is the case where you have distinct real roots. So this quadratic equation happened to give you two distinct real roots, but you know from algebra that you might have repeated roots and you might have complex roots. And we'll look at all those cases. But if for distinct real roots, then your solution will have two roots, R1 and R2. And those the solution will be just the sum of those two. Now, why does the sum work? Like, we know that each of them individually solves the homogeneous equation, but how, can we check that the sum of those two will also satisfy the differential equation? So that's this. Well, maybe I should do it down here. So I'll say, okay, I'm going to prove that statement. I'll just write a little calculation here to show that we can see that the sum of two homogeneous solutions will also satisfy the differential equation. So let's say, we have x1 and x2 are homogeneous solutions. What does this mean? This means that you have A x1 double prime plus B x1 prime plus C x1. I'll just make some labels. So I'll just say that let's the book says this, but let's call this your x1. Let's call this your x2. So we have two homogeneous solutions. I'm just labeling them as x1 and x2. And so given that they are homogeneous solutions, we know that when you plug them into the original differential equation, you'll get 0. And the same idea with the other homogeneous solutions. So we have these where the ones here are now 2's. Now the question is, does x that's built off of, like, I'll just say C1 x1 plus C2 x2, right? That's like this statement here. Does this also satisfy? the homogeneous ODE. And you can easily, let's plug into C. So I'm just going to plug in this. So we know these two are true. The first homogeneous solution will satisfy the differential equation. The second homogeneous solution will also satisfy the differential equation because we know we forced it. We found these R's that would force this to satisfy this differential equation by plugging it in. So we know those two separately should work, but the sum of those two, will that work? You just plug in to see if that will be the case. So what that means is I'm going to go back and plug it into this differential equation up here. So it's going to be A times, I'll just use green on this so that you'll see clearly that, so I'll just say, we're going to say A times this solution, but then that's going to be double primed plus B times the solution prime plus C times the solution. And well, I'll just continue to, I'll just do this. And then eventually, if I get this left-hand side, this is the left-hand side. If I get this to equal 0, then we're done. So the only thing that might be confusing here is this statement that says that this whole thing in the parentheses is double primed. That's like just saying I want to just take the derivative of this whole expression right here. But this expression right here is just like saying C1 times x1 plus C2 times x2. Can you just take the derivative of that? That's just the same as C1 x1 double prime, because C1 is just a constant, plus C2 x2 double prime. Because this thing that's in here, you could think of it as kind of, I'll just write it on the side here. This thing right here is kind of like thinking of it as, if I gave you like 2x plus, I don't know, 5 x, I don't know, 2x squared times 5x, and then I have a prime on it, let's say, then that's like saying just take the derivative of each of these. So it's just going to become like 2 times the derivative of 2x is x squared is 2x plus the derivative of 5x is 5. So it's just the fact that the derivative operator acts linearly to each of the terms in here, and the C1 and C2 are constants. So if I say take the second derivative of this expression, it's just saying take the second derivative of each of these terms, and it's just C1 x1 double prime and C2 x2 double prime. Same idea with the other one, except for this one's just prime. So it's going to be C1 x1 prime plus C2 x2 prime. And then this one is just going to be nothing else. So it's just going to be copying that. And then we're going to continue and check whether this is going to equal 0. What I'm going to do is distribute the A and the B and the C, but I'm going to rearrange. Well, we can just do it right away first. So I'll just say C1 x1 double prime plus AC2 x2 double prime plus BC1 x1 prime plus BC2 x2 prime plus C times C1 x1 plus C times C2 x2. And then I'm going to rearrange the terms. And then, so what I'll note is that there are a bunch of terms that have C1s in it. So this term has a C1 in it, this term has a C1 in it, and this term has a C1 in it. And then there's a bunch of terms that have C2s in it, C2, C2, and C2. So I'll just consolidate and say the terms that have C1, I'm just going to say, since they all have C1, I'm going to factor out a C1. And then this first term will just have AX1 double prime, plus this second one have BX1 prime, and this one will have CX1 after you pull out a C1. Then similarly from all the red ones, you'll have a C2 that you can pull out. So the first one has an AX2 double prime, the second one's a BX2 prime, and then this one's going to be a CX2. And then we notice that this, I'm going to underline in blue, and this I'm going to underline in red, are exactly these two statements up here. We know that we know that x1 and x2 are homogeneous solutions. So we know that if we plug them into this differential equation right here, then we get 0. And so that means that this expression here is equal to 0. And this expression here is equal to 0. So you end up getting that you have 0 plus 0, or I'll just say C1 times 0 plus C2 times 0, coming from the fact that this one is the blue one, and this one's the red 0. And of course, this just equals 0, which confirms our claim that the sum, so when you take the solution x1 and x2 and just add them together with some different constant in front of each of those, does indeed satisfy the homogeneous equation. So not only do each of these x1 and x2 separately satisfy the differential equation, the sum of them, and so if you take in linear algebra, then it would be called the linear combination of the two homogeneous solutions also satisfies the differential equation. And so it's the most general way to write the homogeneous solution in the second order case is you get multiple separate homogeneous solutions, but the general homogeneous solution is just going to be the linear combination or the sum of both of those. And there was nothing in this analysis that required C1 and C2 to be equal to each other. Even if they weren't equal to each other, you'd still get C1 times 0 plus C2 times 0, and those zeros would just cause this expression to become 0. There was no requirement that the C1 and C2s had to be the same. And so they may be the same, but the good practice is to not assume anything and leave them as not necessarily the same if they happen to be the same when you're solving. So in general, you would find C1 and C2 by applying 2 initial conditions instead of 1, because you have 2 unknowns in this case. And then you may end up getting C1 and C2 are both the same, but you don't assume that ahead of time. And there was no requirement that they had to be the same in order for this expression, which is the linear combination of C1, X1, and the two homogeneous solutions, to satisfy this homogeneous differential equation. So now that we are convinced that, you just get 2 homogeneous solutions and you just add them together to get the general homogeneous solution, we'll just use that to find the solution to all these differential equations. So let's do this initial value problem, but I'm going to also make a note here that there is a pattern that you'll see with these characteristic equations. In the end, because of the chain rule and how, you pop out r squared or an r, depending on if it's a second derivative or first derivative, the way you can get to the characteristic equation right away without having to do all that work that we just did before is to just notice that you can look at this differential equation right here and just immediately get to the characteristic equation by seeing that it's going to be a times the x double prime is going to pop out 2 r's because of the chain rule, and so this will be r squared. And then b, and there's an x prime, is just going to pop out an r, so that's like this r right here, so that's going to be br, plus c times x, but x is like the 0th derivative, which means that you're just, so if you think about it, then it's going to be like, oh, you could do this. So b times r raised to the 1, which you don't have to write, but I'll just write. And then c r raised to the 0 if you want, which is equal to 0. This is the characteristic equation. But of course, it's the same as ar squared plus b to the r, because r raised to the 1 is just r. And then r raised to 0 is just 1. So this is just c. So basically, the order of the derivative is the power of on the r. So if you have second order derivative, that's an r squared. A first order derivative, that's an r raised to the 1, which you can just write as r. And then x raised to no derivative, that's like 0 derivative. This is 1 derivative, this is 2 derivatives. So 0 derivative means r raised to the 0, which is just a constant. So that's an easier way to get to the characteristic. Of course, this is the same as this. So you can see that you don't have to go through all of this. You can just immediately get the characteristic equation from reading off. Basically, the A, B, and C's are the only thing that's going to change. And so that's consistent here too. So if you did it with doing that, using that here, then this is A times X double prime, but that's just one. So just all your X double primes and X prime and X's become, so I'll just say X double prime becomes R squared, X prime becomes R, and X becomes 1. And so here your characteristic equation would end up becoming R squared minus R minus 2 equals 0, which is the same as what we got down here. So we're going to use that approach from now on. So for this one, the characteristic equation is going to be just a simple, I'll just say R squared minus 4R plus 3. That's it, equals 0. And of course, this is factored, can be factored to R minus 3 and R minus 1 equals 0. Therefore, you get 2 solutions. You get 3 and 1 for your roots. And we know that your solution, in your general solution, we just verified before, will be the sum of C1 e to the 3t plus C2 e to the t. This is the general solution. And general solution because you still have your C's in it. So an observation here I'll make is that in the past, our general solution had just one C. But in second order differential equations, you have 2 C's. You have a C1 and a C2. And we'll do third order differential equation, which have a third derivative, or a fourth order differential equation, or fifth order differential equation, where you might have like, X triple prime, X quadruple prime, or X 5 primes. How many arbitrary constants do you think they'll have? You'll have 3, 4, or 5. So you might have C1, C2, C3, C4, C5. It just is going to be the same number. So the number of homogeneous solutions and each of them will have some different arbitrary constant multiplied to it. Those are consistent with the order of your derivative of your differential equation. So second order will have 2 homogeneous solutions, each having different arbitrary, so 2 arbitrary constants. First order, we only had 1 homogeneous solution with only 1 arbitrary constant. Third order will have 3. Fourth order will have 4. And so the issue is now that you have 2 arbitrary constants, C1 and C2, in order for you to find, solve an initial value problem to solve for C1 and C2, they're basically 2 unknowns. So you need 2 conditions. And generally they give you a initial condition on the original function x and an initial condition on its derivative x prime. You've seen second order differential equations in probably Calc 1, because like acceleration, you had acceleration is equal to negative 9.81 or something like that. And then you take the integral to get the velocity, but that popped out an integration constant. And then you take an integral of that and you got the position function, and that popped out another integration constant. And the first integration constant was like your initial velocity, and your second one was like your initial position. And that was, that's not necessarily the same. And that's why your C1 and C2 won't be necessarily the same. And you always get 2 integration constants when you're trying to go from acceleration to position, right? You always get 2 integration constants because you're going from acceleration to velocity. You get 1 integration constant, and then to position, you get another integration constant. So you always get 2 arbitrary integration constants going from acceleration to the original function. Acceleration is second derivative of position. So you've seen this before, but those equations were easy because it was just x double prime equals a constant. This is a second order equation as well, but it has a blend of second derivative, first derivative, and the actual function versus the, position or motion function would have just been like something like this. And you just take the integral and integral. This is a very easy second order differential equation, but you've seen it and seen 2 integration constant pop out. Same idea here. You would expect to have 2 integration constants pop out. I mean, we're not doing any kind of integration here, but the idea of going from a second derivative to the original function uh, in spirit is like taking two integrals. I mean, we didn't do it here, but your solution should be sort of gonna give you like two arbitrary constants. So this is why we have that. You have two conditions, so we're just going to use both of them. You have the one condition, which is this orange one, and then we're just going to plug that in. So that just says that we have this is equal to 1 whenever you make your t equal to 0. So that means the e is going to be raised to 0. So this is just like saying 1 is equal to C1 plus C2. This will not give you C1 or C2 right away, but it gives you some kind of relationship between the two. And we're going to use that in combination with the other initial condition, which is the initial condition on its derivative. And that's going to require us to compute the derivative of our general solution. So I'll just bring this down and say, okay, what's x prime of t? X prime of t is going to be 3c1 e to the 3t because of the chain rule, pull the 3 down, plus this one c2 e to the t. That's just the derivative. We need the derivative because we're going to plug this initial condition in. So from this statement, we can say now the derivative is equal to 2 whenever your t is equal to 0. And this is going to give us 2 is equal to 3c1 plus c2. And you can solve this equation simultaneously with this equation. It's just solving a system of differential equation, a system of not differential. They're just algebraic equations. Their unknowns are C1 and C2. You have two equations. So you can I'll just do this. I'll just do elimination. So you just take this one, and then you take this one, and then you just say, this is a system. Why don't I subtract them? So I'll just say this purple one gets subtracted by this orange one. So 2 minus 1 is 1 is equal to 3 minus 1. C1 is 2C1. And then I subtracted so that the C2s go away. So these go away. So this gives you that C1 is equal to half. And if C1 is equal to half, I'll just note that you could use either of these, right? The idea is you do elimination, get one of them, and then you can use that to solve. But the orange one looks easier than this one because this is just 2 added. So you can see immediately that if C1's a half and you need them to add up to 1, then C2 must also be a half. So you've got your two I mean, in this case, it turned out that they were both the same, but in general, they may not be. And so you'll end up with your solution to the initial value problem is half e to the 3t plus half e to the t. Okay. Again, you have two arbitrary constants. You need two initial conditions, and they usually give you it for the function and its derivative. That's called an initial value problem for second order equations. You may have boundary value problems where they give you two conditions on just x, but not the derivative. And maybe they might be that you're just saying find a solution where this differential equation is satisfied with two known values for x at boundary points of some interval. That's called a boundary value problem. But it's still consistent with this idea that you need to have two conditions, whether it be one on the function and its derivative or two conditions on the actual function. You have two unknowns because you have C1 and C2. So you need something, either boundary values at two ends of some interval or initial conditions on the function and its derivative. So that's why either way, a second order differential equation is two arbitrary constants. You require two pieces of information to solve for those two arbitrary constants for a general from the general second order differential equation solution. So that was case 1, where you had a characteristic equation with two distinct roots. You can imagine, let's just skip this and just go and look at this problem immediately, and I'll scroll back up. But This one, the characteristic equation is r squared minus 6r plus 9 equals 0, which factors to r minus 3 squared, because it's a perfect square here. So it's going to equal 2 factors of r minus 3 is equal to 0. So your r is equal to 3, but it's a double root. From what we know before, the general solution to this would be equal to, for sure, one of them will be C1 e to the 3t. But usually the other one was different. So it would be C2 times e to the other one, right? But they're both 3. So you might think, oh, do I just say C2 e to the 3t? But this is like redundant because you could just factor out an e to the 3t and then combine the C1 and C2 into another arbitrary constant. And you don't have two distinct homogeneous solutions. You still just have one. So it turns out that one of them for sure is what we expect, C1 e to the 3t. The other one, it's redundant to just say C2 e to the 3t. The other one will always be the same one, e to the 3t, but with a t multiplied. We saw something like this before where for first order equations, it was something about like the coefficient in front of the x and the coefficient in front of the t on the e to the t, but that was not even a homogeneous equation. That was a non-homogeneous equation. And if they were the same but opposite signs, you had to multiply by t. This t, and then I justified that using the integrating factor. I can also justify why the second homogeneous solution would have to be multiplied by t using a more advanced method called reduction of order. But I'm going to do that a little bit later. So I'll just have to let you revisit that. We'll revisit this, this fact multiplying by t, why that makes sense. But the punchline here is that if you have a repeated root, one of them will be this, the other one will have the t that's multiplied to it. And then, of course, the solution in the end is just the sum of both of those like this. So yeah, I have office hours today at 4 o'clock, and I can, we can work through problems that will be similar to the test problems. And then there's office hours on Friday as well. And that's in Clements, but I'll send out a poll for people who might want to participate in voting which room we like, whether it's this one or the original room. There's also a room next door to ours in Clements that is bigger. So I'm guessing people who wants Clements would probably prefer that room. But I'll send that poll out.
Next month or so.
Okay.
I'm just gonna be out for a few days due to that.
Okay. Yeah, thanks.
Yeah, thank you.